still we're still working with the, of course, the production function using this table, and we're going to draw isoquants. Now, actually, what actually do we mean when we say an isoquant? Isoquant means same quantity, no change in the quantity, okay? So it is the curve that shows all of the combinations of labor and capital, see labor along the horizontal axis and capital along the vertical axis. It shows all the combinations of labor and capital that can produce the same quantity of output, okay? Here, we're gonna draw some isoquants, okay? Now, if we come over here to this table, those numbers inside the table here represent, of course, the quantities, the amount of outputs. So if we take, for instance, Q equal 15. Now, what are the combinations of labor and capital that can produce Q equal 15? Well, Q equal 15, we can have Q equal 15 by employing 12, machine hours per day and 6 labor hours per day. Also, we can obtain 15 by employing, 12 labor hours per day and, 6 machine hours per day. So these are the combination that eventually will give you, the same quantity produced, which is 15. So here, when we can draw the isoquant, as you can see, at point A, we have 12 units of capital and 6 units of labor. At point B, we have 6 units of capital and 12 units of labor. And when we draw this one, we get isoquant. So Q1 equal 15 isoquant. When we move up, we come up with higher level of output. So also we can draw Q equal 25. We can draw Q equal 162, or we can draw, any level of output, Q equal 30, or Q equal 48, or 162, and so on and so forth. Okay, and when you draw, let's say Q isoquant of 30 is going to be above isoquant of 25, and isoquant of, let's say, 75 is going to be above isoquant 30, and so on and so forth. Okay, so here, the isoquants increases. Okay, now let's look at the marginal rate of technical substitution. What actually do we mean by this? The marginal rate of technical substitution of labor for capital, denoted by marginal rate, MRTSLK, marginal rate of technical substitution, labor for capital, measures how steep an isoquant. Remember, it tells the rate at which the quantity of capital, this is along the vertical axis, can be reduced, okay? The quantity of can be reduced, okay, for every 1 unit increase in the quantity of labor, holding the quantity of output fixed, okay? Holding the quantity of output fixed. The figure alongside here, this figure here, illustrates the marginal rate of technical substitution labor for capital. Look over here. Now, along Q equal 15, isoquants, notice that at point A, okay, here, we draw a tangent line at point A. The slope of this tangent line at point A, of course, is greater than the slope of the tangent line at point B, is greater than in absolute value, because it's negative, okay? So why here is greater than? Because it is steeper than this. So, the slope of the straight line drawn at A, of course, is greater in absolute value than the slope of the straight line or the slope of the tangent line, drawn at point B. Okay? So what that means? So, for instance, to take, to find the slope of the tangent line at point A, in a curve like Q1 equal 15, all we have to do is to take 2 points along that tangent line and then find the slope. And the slope is equal rise over run, the change of the variable along the vertical axis over the change of the variable along the horizontal axis. This is, the definition of the slope, which is equal to the rise over the run. So, of course, now here, if I take 2 points, won't get precise value, because, this figure is not drawn, based upon precise units, okay? That's why I just, took values, okay? But assuming that the values of the slope of the straight line over here must be higher in absolute value than the value of the slope of the tangent line over here at point B, okay? That is the assumption, okay? So now what we see over here, of course, to just, let's say here, at point A, the slope of the line tangent to the isoquant is greater than the slope of the line tangent to the isoquant at point B. That is what I said. This is because the tangent line at A is steeper than the one at B, okay? So in absolute value is bigger, but however, it is negative, okay? It is negative. Now, goes downward sloping. This is because, of course, this is because steeper. Say that the slope of the tangent line at point A is minus 1.8. It's not 1.8, but I said, I just assume it is minus 1.8. And this number should be greater than, in absolute value, than the slope at point B. So I said, let's say the slope is equal to minus 1.8. Therefore, the marginal rate of technical substitution labor for capital is equal, 1.8. Okay? 1.8. This means that starting from this point at A, we can substitute 1 man-hour, okay, of labor for 1 point machine hours. So the firm, at point A, it can, make a substitution, 1 man-hour of labor for 1.8 machine hours of capital, okay? And output will be the same, no change in output. Once the firm, does the substitution of 1 man-hour of labor for 1.8, machine hours of capital. Now, of course, now the same thing at point B, if, I did not assume that, I could say, for instance, assuming that the slope of the tangent line at point B is, let's say, minus 0.6, okay? Should be less than, the slope at point A in absolute value. So let's say it is minus 1.6, minus 0.6, okay? Then we say the marginal rate of technical substitution labor for capital is equal 0.6, which means that the firm, can substitute 1 man-hour, okay, for 0.6, 1 man-hour of labor for 0.6 machine hours of capital. So notice that as we move down along the isoquants, you're moving down, okay, the slope of the isoquant decreases in absolute value, of course, from 1.8 to 0.4. It decreases in absolute value. This means that marginal rate of technical substitution labor for capital gets smaller and smaller, okay, along this isoquant, which is convex to the origin, which is what? Convex to the origin, okay? This property is known as diminishing marginal rate of technical substitution, okay? When the marginal rate of technical substitution labor for capital, decreases, okay, as we move along the, the isoquant, then we exhibit or we experience a property that's called diminishing margin rate of technical substitution. Therefore, when the isoquant has this property of diminishing margin rate of technical substitution, that is, when margin rate of technical substitution decreases as the quantity of labor increases, the margin rate of technical substitution decreases, going from A to B as the units of labor increases. As we move this way, 6, 12, 18, so the units of labor increases. Okay, then the isoquant is convex to the origin, as you can see, is going convex, not concave, however, it's convex. Its back is toward the origin of the plane over here. Okay, now we want to, of course, see that we have a precise, connection between the marginal rate of technical substitution and the marginal products of labor and capital. So we're going to derive a formula that, shows that the marginal rate of technical substitution of labor for capital is equal to the ratio of the marginal product of labor over the marginal product of capital. So remember, when we change the quantity of labor by delta L, units of labor, and the quantity of capital by delta K, units of capital. So we change the quantity of labor by, delta L, units of labor, and the quantity of capital by delta K, units of capital. Of course, then as a result of this, change, we're going to come up with the change in output. The change in output would be as follows. Delta Q, which is the change in output, is equal to the sum of the changes in capital, okay, and the change in labor. So the change in Q, which is the change in output, is going to be equal to the change in output that results from a change in the quantity of capital plus a change in output that results from a change in quantity of labor. Okay? Great. So the change in output from a change in the quantity of capital is equal delta K times MBK. And the change in output from a change in the quantity of labor is equal delta L times MBL. So this is, the change in the quantity of output. Okay? The change in output is equal to the sum of those changes in the quantity of capital and the quantity of labor. Great. Now, remember, this is an isoquant where Q is equal to 15. Along a given isoquant, output stays the same. Okay? So there is no change in output. You remember, an isoquant is a graph or, as a graph that shows, a curve that shows all the combinations of labor and capital that give you the same level of output, or that produce the same level of output. Okay? Now, so along this isoquant, Q is the same, which is 15. No change in Q. Okay? Great. So delta Q along a given isoquant is equal to 0, because delta Q is a change in Q. Okay? So the change in Q, there's no change in Q, therefore it is 0. So it's equal to those, delta K times MBK plus delta L times MBL. Or if we played with this one over here, this becomes, if you move delta K MBK to the left side, we come up with minus delta K MBK is equal to delta L MBL. So now if we rearrange this one here by dividing each part of this by, of course, delta L, MBK, we come up with what? Dividing both sides by delta L MBK, okay, we get minus delta K over delta L equal minus MBN over MBK. Now remember, the negative of the slope of any point along the isoquant gives you the marginal rate of technical substitution, the negative of the slope. So over here, for instance, we said before that the slope over here, we assume that the slope over here is minus 1.8. So at point A, we said, okay, that at point A, the marginal rate of technical substitution is equal negative, okay, minus 1.8 becomes 1.8. So the marginal rate of technical substitution at point A, as we said before, is equal 1.8. So the marginal rate of technical substitution is the negative of the slope of the isoquant. So this is here minus, which is minus delta K over delta L. This is the slope of the isoquant. This is the slope, of the isoquant at point A or at point B, the slope of the isoquant, okay? So the negative, this slope is the marginal rate of technical substitution. So we just see that minus delta K over delta L is the negative of the slope of the isoquant, and the negative of the slope of the isoquant is equal marginal rate of technical substitution. Therefore, marginal rate of technical substitution of labor for capital is equal MBL over MBK. That is equal to the ratio of the marginal product of labor to the ratio to marginal product of capital. So this is a nice formula that relates the marginal rate of technical substitution to the ratio of marginal product of labor and marginal product of capital. Okay, now solving problems of chapter 6, we're going to do problem 3. Okay, for the production function Q equals 6L squared minus L cubed, fill in the following table and state how much the firm should produce so that we have 4 parts of that problem. Average product is maximized, marginal product is maximized, total product is maximized, average product is 0. Let me just state something over here. Remember, let me just do over here. Remember, average product, when of course the production function is a function of one input, let's say labor, okay, and this is here, okay. When the production function is a function of one input, usually it is called total product, total product function, okay. And because labor is the only factor of that production function, then it is called total product of labor. Okay, so total product of labor is the same as a Q, which is the same over here, which is 6L squared minus L cubed. So when the production function is a function of one input, it is called total product function. Okay, if it is a function of labor, then total product of labor, which is the same thing as a Q. Okay, now the average product of labor, is going to equal total product of labor over L, or Q over L. Okay, this is the equation of average product of labor, and we said average product of labor because the variable or the input is labor. Okay, so total product of labor, which is the same as Q over L. Okay, so now what we want is we're going to fill out this table. Now average product is let's fill out the table first. We have L ranges from 0 units of labor all the way to 6 units of labor. Now Q, we just plug, this is here. For L equals 0, for instance, 0 squared minus 0 cube. What do you get here? You get 0. As we got here, 0. Now we take the other one. Take the other one, okay? Just to show you exactly how to do that. 1 squared minus 1 cube, which is equal 6 minus 1 is equal 5, as you can see, and so on and so forth. We can fill out the Q, which is the total product of labor. Okay. Now, what about the average product of labor, which is Q over N, or TPL over N? So we just fill out this table, the same as we did over here. For instance, over here, Q is what? 5, okay, total product when Q equal, of course, here 0. When Q equals 0, total product is 0. Okay? Now, an average product when Q equal 5, which is 5 over 1, which is 5. Okay? Now, the average product when L equal 2, we just divide Q 16 over 2, 8. When the average product when L equal 3, we just divide 27 over 3, we get 9. When L equal 4, we divide 32, which is the total product of labor, over 4, we get 8. And then when L equal 5, we divide total product of labor, 25 over 5, we get 5. And then here we divide 0 over 6, we get 0. Okay? Now, what about the marginal product of labor? You remember, marginal product of labor is equal a change in Q over a change in M, which is equal Q2 minus Q1 over L2 minus L1. Okay? This is the marginal product of labor. Okay? So what we do over here, we got here, for instance, for the first unit is going to be equal what? Q2, which is equal for the first unit. Okay? You know, when, of course, L equal 1. It's going to be equal 5 minus 0 over 1 minus 0, we get 5. Let's get 5. What about for the second one? For the second one, okay, for L equal 2. For L equal 2, it's going to be equal Q2 16 minus 5 over 2 minus 1, which is equal, of course, 8. 16 minus 5 over 2 over 1, we get, of course, 8. Okay? So here we get 16 minus 5 over 2 over 1, we get 11. Okay, I'm not talking about, we get 11. Okay, we get here, sorry, 11. Now I'm just looking at here, I should be looking at marginal product of labor. Now the same thing, we get here 11. Now the same thing when Q equal 3. When L equal 3, then, you know, the marginal product of labor is going to be equal, of course, 27 over minus 16 over 3 minus 2, which is 27 minus 16 over 3 minus 2, we get 11. Okay? But the same thing when L equal 4. When L equal 4, it's going to be equal Q, 4 minus Q 3 over 4 minus 3. Q4 here, 32 minus 27 over 4 minus 3. What do you get over here? You get 5. Okay? And we can do the same thing using this formula. So for L equal 5, Q5 minus Q4 over 5 minus 3. Over 5 minus 4. And we come up with, minus 7. Okay? Here now. So this is how we calculate the marginal product of labor. Okay? Marginal product of labor. Now, this is the easiest way to do that. Of course, we can use the calculus to do that. It's not that, it's not, that hard, but we can do the calculus if you want, okay? So now we get the values of the total product of labor, the average product of labor, Q over L, average product, Q over L, and the marginal product, of course, which is delta Q over delta L, which means the derivative of Q with respect to L, okay? We can, find the derivative of that easily, Okay. Now, the first question A says, how much the firm should produce. Let's look at the value of the input, okay, so that average product is maximized. Well, if you look at the average product, which value is maximized over here? Okay, now we can see here is maximized when Q. So here we say, A here, average product of labor is maximized when, of course, when the value of average product of labor is maximum, is the maximum. So it is 9. So when n equal 3, over here, when n equal 3, the average product is 9. Now, can we can use the a certain concept. Remember the relationship between average product and marginal product. Okay, is very clear. When the marginal product of labor is above the average product of labor, average product of labor is increasing. When the marginal product of labor is below the average product of labor, then average product of labor is decreasing. And the average product of labor is maximized when the average product of labor is equal the marginal product of labor. We can do that easily. So we can do A, okay, here. We can, okay, A here, we can solve A by equating average product of labor equal marginal product of labor. Now, when we do that, equating average product of labor with the marginal of labor, this implies average product of labor is maximized. So average product of labor, it is Q over L. And over here is, delta Q over delta L. Okay? So Q over L, this is the Q over here, 6 L squared minus L cube over L is equal the derivative of Q with respect to L, which is equal 12 L minus 3 L squared. So what do you get over here? You get here 6 L minus L squared is equal 12 L minus 3 L squared. So let's simplify this equation over here. Okay, we can have 3 L squares minus L squares is equal to 12 L minus 6 L. So we get here 2 L squares is equal 6 L, which is equal over L here, over L over here. We get here 2 L, of course, equal 6, which is L is equal 6 over 2, which is equal 3. And the same thing we get over here, 3. So we can use either calculus or we use the usual way that we did over here from looking at the values of the table. Okay? Now, we need to find, of course, let's do the other part of the questions over here. There is this one over here. Okay. Now part B. Part B. Part B, of course, says, we need to say that, we need to show how much the firm should produce so that marginal product is maximized. And that's the marginal product is maximized, okay? If you look at over here, of course, using the table, marginal product of labor is maximized when L is 2 and 3. Okay, when L is equal to 2 and 3, because that will give you the highest value of margin product, give you the maximum value of margin product. So when L equal to or 3, we get the maximum value of margin product of labor. Now, we can do that mathematically, okay? We can solve this algebraically. Okay, we can do that algebraically. Of course, how we do that? Of course, if you want the margin product to be maximized, the margin product is a derivative. Okay, so we want the derivative to be maximized. That means we need to find the second derivative. Okay, so now marginal product of labor is equal. We get the derivative over here. We get it 12 and minus 3 and square. This is the marginal product of labor. This is the marginal product of labor. So now, we want this marginal to be maximized. So what we do here, we need to find the second derivative. So here we find the first derivative of Q, the total product labor, to get the marginal product. Now, in order to have the marginal product to be maximized, we need to find the derivative of the marginal product and set that equal to 0 to find, of course, the critical points. So now, we get the derivative of this, M, P, L, derivative of this, which we get what? The same thing over here, d m p l over dl, the derivative of the marginal product labor with respect to 12, which is equal 12, derivative of this 12, minus, of course, 6l. Okay, set that equals 0. Set this equal to 0 to find the critical values. So we got, it's 12 minus 6l equals 0. That implies, of course, 6l is equal to 12, which implies l is equal to 12 over 6, which is equal to. This is a good question. This is a right question, and this over here. So over here, the maximum value, of course, is 2 or 3 labor. That will give you a maximum value of marginal of labor. Over here, mathematically, the maximum value is 2. So L here is equal to, will give you the maximum value of course, the maximum value of marginal product of labor. Now, let's look at the second question, which is what? Total product is maximized. Well, total product is maximized. Of course, let me erase over here. C, total product is maximized. The total product, as we said, it is Q. Looking at the table, we see that total product of labor, which is Q, is maximized when what? When L equal 4. When L equal 4, get 32, this is the maximum value of Q. So when L equal 4, Q equal 32, and that will give you the maximum value of total product value. Then is maximized when L equal 4. When L equal 4, we get 32. Okay? So L equal 4, that implies Q is equal 32. Now, okay, great. Now, D, it says, how much the firm should produce so that average product is 0. Now, average product, this is average product. Average product of labor equals 0. Remember, average product of labor is 0 when what total product is 0, because average product of labor is equal total product of labor over labor. So that, okay, what this implies here, average product of labor equal total product of labor over L, which is equal to the same thing as Q over L. So average product of labor is 0 when the numerator is 0, which is when Q or total product labor is 0. So average product of labor equals 0 when total product of labor equals 0. Well, total product of labor is 0, that's Q, when what? When L equals 6. So total product of labor equals 0 when L equal 6. When L equals 6, total product is 0. So average product is 0 when the numerator of that equation is 0. The numerator is what? Total product of labor. So total product of labor is 0. That implies it is 0 when what? When L equals 6. So therefore, average product is 0 when L equals 6. Okay, now we're going to solve problem 9 in chapter 6 concerning the concept we have already discussed. The problem says, suppose the production function for automobiles, of course, is Q equal LK, okay, where L is labor and K is capital, where Q is the quantity of automobiles produced per year, okay? Now L is the quantity of labor and K is the quantity of capital, okay? Labor is, the quantity of man hours per year, and capital is the quantity of machine hours per year. Now, part A, it says, sketch the isoquant corresponding to quantity of Q100. So to sketch the isoquant, we're going to do the following, okay? We're going to have L, K, we're going to have Q over here, okay? Q is what? Is 100. Now you ask yourself the question, what are the values when you multiply them with each other? You come up with 100. I get, 10 and 10. We get 5, we get 20, we get 20, we get 5. These are the numbers that, of course, when you multiply them, you come up with the quantity 100. So I need to sketch the isoquant. Okay, let me, do it over here. Okay. So you have, of course, K over here, L over here. Okay. K is along the vertical axis and L along the horizontal axis. Now we get 520. This is 5. Okay, this is 10, and this is here 20. So 5, 10, 20. This is over here, 5, 10, and this is over here, 20. Okay? Okay. Here you go, 10, 10, this is 10 over here. This is a value over here. I hope it is, it's not going to be precise, but at least it will show you, the sketch. 520, labor is 5, and 20 is the capital. So we come over here, okay? That's what you get over here, okay? And you get over here, okay? Okay, now what we're gonna do, we're going to connect those points. We need to connect those points, okay? Connect those points here. Okay? So as you can see, this is Q equal 100. Okay, this is the isoquant of the quantity equal 100. Now, great. So we sketch the, the isoquant. Okay, great. Now, what is the general equation for the isoquant corresponding to any level of Q? Okay, the general equation, this is B over here. What is the general equation? Of course, to do that, we just we have the equation over here. Q is equal LK. Okay, so we solve this one for K in terms of Q. So we'll come up here. K is going to be equal Q over L. This is general equation, of course, for the isoquants. Of course, if you're talking about a specific, for a specific output, value of output, all we have to do, we find the general equation, and then when we replace or substitute for Q the value of Q. Okay. For instance, if I want to find the equation for the isoquant corresponding to Q equal 100, so what I do, it's going to be like this. Let's say here P prime. Okay, it's going to be equal to K is equal 100 over N. So this is the isoquant equation corresponding to Q equal 100. Okay, C is saying, does the isoquant exhibit diminishing marginal rate of technical substitution? Remember, we defined that a marginal rate of technical substitution is the negative, is the absolute value, is the negative of the slope of the slope of the isoquant at each value. For example, you have over here, you have value over here. This is the slope of the tangent line at A here, at B over here, at C over here. Okay? So as you can see here, the slope of the tangent line at point A along the isoquant here is greater than of course, the slope of the tangent line, drawn at point B, tangent to point B. Also, the slope of the tangent line at B is greater than, in absolute value, is greater than the slope of the line, of the tangent line drawn at point C. Therefore, as we move along the isoquants, as L increases, and Q decreases, what we notice? We notice that we have a diminishing marginal rate of technical substitution, okay? Because the slope over here in absolute value is greater than over here, is greater than over here. So the slope is decreasing. So we have a diminishing marginal rate of technical substitution, of course, diminishing margin rate of technical substitution because the slope decreases. Another way we can prove this, of course, is that the isoquant is bowed in toward the origin. So because the isoquant is convex to the origin, or bound in toward the origin, then of course the isoquant exhibit a diminishing marginal rate of technical substitution. Okay, and this is basically the easiest way to prove that this isoquant is exhibit a diminishing margin rate of technical substitution because it is, it is bowed in toward the origin or convex to the origin over here. Okay, when it is back is, toward the origin, it's like this. This is the graph of the isoquant that is what exhibit or show a diminishing margin rate of technical substitution when it is bowed in toward the origin or convex to the origin, then will exhibit this phenomenon. Or, you can say that the slope over here of the tangent line over here is greater than in value than over here, and here is greater than the slope over here in value. Then it is diminishing as, L is increasing, along this isoquant, we can see that diminishing marginal rate of technical substitution.